Okay, guys, so in this lesson, we're gonna talk about refraction of waves. Okay, so you guys probably already know refraction of waves from light. You might still remember it. So I'm just gonna quickly draw over here. So what happens with light if we say if there is a light coming, say, from air going into, say, water, it's gonna bend closer to the normal line, right? And then we have another one is, well, if it's going light going from, say, water or say plastic going into air, they're going to be bending away from the normal line, right? So those are the two refraction we've learned before, and we were particularly talking about light wave. So according to the optical density, and then we can calculate the angle by using this equation. N1 sine theta 1 equals to N2 sine theta 2, right? Okay, so if you forgot about it and go back, have a look at the notes of light wave, how it refracts, and then we're going to be linking that into today's lesson, okay? So today we're going to look a bit more in general. So how does a wave refract? So all types of wave refract, not just light wave, sound wave, say water wave, they all refract, okay? So in particular today, we're going to use water wave as a demonstration, but it's exactly the same as any other wave, okay? All right, as you know, all waves have a wavelength over here, right? So the wavelength, and then this is the wavelength that's coming. Okay, say this is deep water going to go into shallow water. This situation is the shallow water is going to go into deep water. All right, so the notes I give you is I draw the water boundary sideways. So basically what you do is you just lift this up. That's going to start to go sideways, okay? The reason why I draw in the notes it goes sideways, and that's because a lot of the questions in the previous years, it has been going sideways. But to be able to, it's easier to understand if I draw it this way, because this is just like how we draw these ones, okay? All right, let's have a look at this one first, and then you can draw this one as well into your notes, and then you can have another look of the one I've showed you over there, okay? All right, say this. Now we got a water wave. First, we're going to figure out which water travels faster, okay? So we look at this situation over here. If you go to the wave, if you go surfing or if you go swimming in the ocean, you'll notice like if very, very far away in the deep sea, the deep water, you can't really see the wave very much because the wavelength is super long. Okay, the wavelength is super long. But when it comes to the shore, the wavelength becomes very short. And that's when the wave is going to bulge up and then dump on you, okay? So what happens is when I go surfing, for example, like when I first started surfing, like I always stay over here and then just get dumped by the waves. And later I've realized is I actually need to surf and paddle all the way to here. And then I wait for the wave to, and then I try to catch a big wave, okay? But I can't stay here. If I stay here, I will never catch any wave because these waves are not breaking. Only when the wave becomes really short and then all the energy got concentrated and then it lifts up and then you slide down the wave. So we stay over here and try to, and then paddle forward, try to catch this wave and go down, okay? All right, so now we've established the wavelength, so lambda 1, lambda 2, okay? And let's figure out, well, if this one have a short wavelength over here, for a water wave, the frequency does not change, okay? And actually, all these situations, the frequency do not change. It's because what is the definition of frequency? Frequency is how many waves happens in 1 second, right? If you forgot about it, have a look at your notes. How many waves happen in a second? Well, if there's one wave coming over here, it's going to become one wave over here. If there are 5 waves coming, and then it's going to land 5 waves over here. So the frequency can't really change, okay? So if the wavelength is really small, say the wavelength is really small over here, so look at the equation, they need to equal to each other. If this side, this is becomes smaller, and the speed must become smaller, okay? So in shallow water, the wave is going to be slow. And then in deep water, the wave is going to travel fast. Okay? And typically these two information actually will be given to you in your questions, but you can see it's actually because this is slow and this is fast. You can know it from the wavelength, okay? You can write this down in your book as well. All right, so now let's have a look what's going to happen. All right, so originally the deep water is over here, right? And then coming here, and then it's going to slow down. say here, imagine this is a marching band. They're all going together here, here, here. But now these guys are going to start to fall behind a little bit, right? It's going to slow down. If it doesn't slow down, it's going to go here, straight line, straight line, straight line, straight line. But it just keep going straight line. But these guys have slowed down. So if I slow down, I'm going to draw back a little bit. You can see this part was this part over here, and it slowed down first. It's going to start to go this way. All right, and then these guys start to slow down. All right, so now there's more slow down. Now there's more slow down. Once it enters the shallow water, it's going to start to slow down. Okay, and then it's going to keep, now all of them has entered here. All of them is going to slow down. Okay, all of them is going to slow down. Okay, so as you can see, I probably should draw this a bit better. So now they've gone to here. As you can see, because of this slowdown, now the direction is also changing. Because the direction of a wave is always perpendicular to the wavefronts. Okay, so what are wavefront? Each line is called a wavefront. Okay, and the direction the wave travel, I'm going to use this red line, is always 90 degrees to the wavefront. Say this is the direction the wave was traveling. Okay, and now you can see, well, because of this slowdown, and now the wavefront has changed direction, and then the wave has changed direction. And now it makes the direction of the wave changes, okay? And you can see this situation is going to be exactly the same as this situation we see from the light topic. When light topic, we say, well, why does that happen? Why does wave change direction? It's because the speed has changed. Well, if the speed changes, why does that change the direction of the wave? So this is the reason why, okay? So it's bending towards the normal line. So if I want to draw a normal line, I can draw a normal line over here, like that. That would be my normal line over here, okay? Incident angle, reflection angle, but we don't need to talk about those two angles at the moment, unless we're going to do some calculations, okay? All right, so I'm going to take this away. So now let's have a look. Over here, I can establish some equations, okay? So say, well, V1 over V2 is going to equal to lambda 1 over lambda 2. The reason for that is because of this. Say V equals to F lambda, right? So the bigger the wavelength, the bigger the speed. Speed and wavelength are proportional. So say this. If you got F V1 equal to F lambda 1, V2 will equal to F lambda 2, right? Okay, and then the frequency we say it's the same because 3 waves coming, 3 waves gonna go this way. Then we can divide them by each other. So V1 divided by V2 equal to lambda 1 divided by lambda 2. Okay, so this is the fundamental equation that we're gonna use over here. And then we're going to link it back to the original equation we had. And we know how this is going to be inversely proportional to the optical density if we remember the wave with light. With light is equal to N2 over N1. Okay? That means the bigger the optical density, the smaller the speed. So these two are opposite to each other, okay? All right, and then we also have that equation, N1 sine theta 1 equal to N2 sine theta 2, and saying N1 divided by N2 equal to sine theta 2 over sine theta 1, okay? So now, over here, that's N2 over N1, so that will equals to sine theta 1 over sine theta 2. Okay, the other equation is V equals F lambda. Okay, this equation will be given to you, this equation will be given to you, and this equation will be given to you as well. So you just need to use it. You don't really need to remember it, okay? But it's better if you can understand this, so that you can use it better, okay? All right, so what is theta 1? And then that is gonna be the angle over here. So that is your theta 1. If we're taking this as angle 1, that's theta 1, and this is theta 2, and that's lambda 1, and that's my wavelength 2, lambda 2. Okay, and then obviously we have speed v1, v2 over here. Okay, so in this particular one, because we're talking about water wave, so there's no refraction index. But if I just change it into, say, this is a light wave coming from air to water, then we're gonna have a refractive index. Okay, all right, so now let's have a look of this situation. Same situation, except now we're going from shallow water to a deep water. Shallow water to deep water is gonna speed up. So it's the opposite of the one we've done before, okay? So let's speed up. How do we speed up? Say here. They're coming. We're just gonna keep going. But now from here, these guys is gonna speed upwards. So it's gonna go forward a little bit, okay? So I just draw a little bit forward, don't need too much. Okay, or I don't draw too long because this is the original length we have. So we're gonna draw to here. Okay, and this one is gonna go forward. Okay, and then it's gonna start to go in this direction. So I should probably draw this just a little bit longer, because that need to be the same as over here. Okay, and then now you can see, because it's bending forward, this gap has increased compared to this gap over here, showing that if the speed increase, the wavelength is going to increase, okay? Again, V equals F lambda. If speed increase, the wavelength is going to increase. Okay, so that is my deep water situation. So if I draw the direction, again, direction is going to be 90 degrees. It's over here. All right, now it's going to become 90 degrees over here like that. Okay, so the direction of the wave has changed as well. So now I can, if I draw the normal line, and this is the reason why the theta 1 and theta 2, now theta 2 is going to become bigger, right? Okay, and then so that is going to be my lambda 1. This is my lambda 2. And there will be a speed v1 over here. There will be a speed v2 over here. Okay, so this is how a refraction of a wave actually works. And because of this, so we got the light refract, okay? All right, so Alright, so in terms of how do we do questions, so I'm gonna run a question with you guys so you can have a look, see how it works, okay? But you make sure you copy this down and understand this. So write this, include also write the notes from your book, okay? So now it gives you a like kind of a comprehensive kind of understanding. If you want, watch this video again, pause and stop and go back, and then if you have any questions, just let me know, okay? Alright, have a good day guys. See you in the next video.